In this subpart of the lecture number 18, we discuss a very interesting topic in small oscillations, which is known as parametric resonance. Okay, sometimes we can call it parametric instability as well. Okay. In usual cases, whenever we talk about an oscillatory system in general, the natural frequency, as we already mentioned in previous lectures, natural frequency omega 0 is determined by the property of the system, right? That means mass, elasticity, stiffness, for example, okay? And omega 0 is supposed to be constant during the motion. That means no condition of motion can alter it. So in another way, we can say it cannot be modified externally without modifying the property of the system. So this is a source property. Okay. But of course, it can be altered if we alter the source property itself, or we modify the nature or the properties of the source. Now, if we consider a system for which the properties of the system is modified somehow, okay, with time, then omega 0 is also modified. That is, if the, let's say, if you are just considering the system of like free oscillation, then omega 0 square is nothing but k by m. So let's say we are taking a system where the system's mass is changing. Let's say something is burning basically while moving, okay, like a rocket or something, we don't know, but this is a problem of changing variable mass. Then of course its omega will be modified because m will be modified. So m will then be a function of time. For that specific case, we should start with this equation ddt of mx dot and not md d2x dt2, that you all know. Then it will be the most general form of Newton's equation, that is the rate of change of linear momentum will be equal to the force. Actually will be proportional to the force, but okay, here we have just written that will be equal to the force, and by suitably choosing the unit of the force, of course, once again. And for that you can know that the Lagrangian will still be written like this: half mx dot square minus half kx square. So in terms of Lagrangian you cannot see the difference, but whenever you will write the equation itself, the equation of motion, you have to keep it in mind that ddt of mx dot will be the rate of change of the momentum, and this is not exactly equal to here m times x double dot. Okay, so then we can write like m as a function of t, and for that in order to simplify this whole equation, or to regain the form of our well-known equation, we will do a trick. That is, we define another variable tau, which will be like time, but it will be a bit different. That means d tau will simply be equal to dt by m of t. Okay, and if we just use that, you can see that ddt will simply be written as dm d tau, and mx dot will simply be written as m dx by m d tau. M will go away, and finally we will be left with d2x d tau 2 plus mkx. This m will be multiplied over here, okay, and this mk will be called then omega square of tau. That will be another frequency. Okay, now finally we can see that the form is reduced just after choosing a suitable variable. Okay, the form is regained. This d2x d tau 2 plus omega square tau x is equal to 0. So we can then say that if we find the solution for this equation d2x dt2 plus omega square is a function, which is a function of t times x is equal to 0, then we are done. Finally, that in this form and in this form, basically whether you are using t or tau, that is immaterial, right? and omega square t can be any function of time. Okay. Now let us assume that omega t is a periodic function. Okay. It is possible that I am changing the property of the source in such a way that omega t is a periodic function with period capital T, which will be equal to 2 pi by gamma. Here, not to confuse with the frequency of the force in the forced oscillation case, this is the frequency of this change of the property of the change of the property of the source or source material. Okay, so then we can easily say that omega of t will simply be equal to omega of t plus capital T, or omega will be equal to omega of t will be simply equal to omega of t plus 2 pi by gamma. Any one of the two is correct, and hence the equation 1 has a form invariance under the transformation t to t plus capital T. So this equation, whether t is equal to t or t is equal to t plus capital T or t is equal to t plus 2t, 2 capital T, the form will always be invariant. Okay, so the form of the equation has a period of t then. Okay, just think about this. Okay. Okay, now if x of t is a solution of the system, then x of t plus capital T will also be the solution of the system. That is also very evident from here, because the form is invariant under this transformation t to t plus capital T. So any solution will be which is true for for time is equal to t will also be true for time is equal to t plus capital T. Okay. As the characteristic polynomial of equation 1 is quadratic, that is important. Okay. All the solutions xt can be written in terms of a linear combination of two independent solutions, x1 of t and x2 of t. Okay. Then, in fact, after time capital T, that means after one period time, okay, one time period, they should be transformed into a linear combination of themselves, right? So basically we know that any solution would be transformed to the same, would be invariant to the solution after some time capital T. So if we just say that the basis for the solutions are x1 and x2 at time is equal to small t, then they will also be the basis for the solutions of time is equal to t plus capital T. So any solution, for example, when they themselves will be transformed, okay, after time capital T, they will also be written in terms of the two basis two base solutions. So that's exactly what is written, that x1 t plus capital T will simply be equal to a1 x1 plus a2 x2, and the same will be for b. Okay, same will be for x2. Okay, x2 of t plus capital T. Now it is always possible, actually it's not always, but under certain conditions that I am not entering here, but you have to think and tell me where. It is always possible to choose x1 and x2 in such a way that the x1 exactly before and after this capital time t, that means at time t is equal to t and time t is equal to t plus capital T, both the solutions of the equations are simply parallel to each other, or simply they are proportional to each other. So that will be given by this type of relations, and same for x2. So mu1 and mu2 are proportionality constants. Okay. Then if we can do that, if we can do this, so this is something if and then type of thing. If we can do, then the most general functions, okay, then the most general function satisfying to this will be given as x1 of t will simply be equal to mu1 times t by capital T pi 1 of t, and x2 will be mu2 to the power t by capital T pi 2 of t, where pi 1 and pi 2 are two periodic functions of time, also with the same period capital T. Okay. So you can understand here, basically we are trying to guess the nature of the solutions. Okay. Now how to show that? Can you have any, I mean, do you have any idea how to show that if this is true, then the most general function satisfying this will be this? Think. Huh? This is also a very, I mean, good brain twister. Okay. Now note that we also have these two equations, because x1 and x2, they also satisfy the base equations. So we have x1 double dot plus omega square x1 is equal to 0, and x2 double dot plus omega square x2 is equal to 0. Then just multiplying this first one by x2 and the second one by x1 and just subtracting them, you can finally conclude that x1 dot x2 minus x1 x2 dot will be a constant in time. That's a fantastic conclusion. Okay. Now this is a constant of motion for this type of situation. Now let's say that, I mean, not let's say, but now let's calculate explicitly this thing. And if you calculate that, if you calculate just by following this algebra, okay, you will see that x1 t plus capital T is, as we have already assumed, that, I mean, our form is satisfying this, x1 at t plus capital T will be equal to mu1 x1 of t, and x2 capital, I mean, small t plus capital T will be equal to mu2 times x2 of t. And then just by calculating their dots, okay, you can easily see that x1 dot t of t plus capital T will be equal to mu1 times x1 dot t. Okay, so although the I mean, if the amplitude, I mean, if the variables, like the coordinates, they are proportional with the proportionality constant mu1, okay, their dots are also proportional with the same proportionality constant. And same thing you can show for x2. And finally you can show that as this is a constant of motion, then this x1 dot x2 minus x2 dot x1 of t plus capital T will simply be equal to x1 dot x2 minus x2 dot x1 at t, right? Because this is a constant of motion, this does not change at any time. So then you can finally write this one is equal to mu1 mu2 x1 dot x2 of t minus mu2 mu1 x2 dot x1 of t. Then you can just take the mu1 mu2 common and you can say this one is t. But you know that by the constancy this one is exactly equal to this one, and that is only possible when mu1 mu2 is equal to 1. Okay. Now further information about mu1 and mu2 can be obtained. Okay, if we note that they are real coefficients. So if x is a solution, then x star is also a solution, and then we can say that mu1 mu2 will be simply equal to mu1 star mu2 star is equal to 1. Okay, and so mu1 mu2 is real, but this is possible this is possible only when either mu1 and mu2 are individually real, or mu2 is equal to mu1 star and mu1 is equal to mu2 star. Because in that case, if mu2 is equal to mu1 star, then this thing will be mu2 will be 1 by mu1, and 1 by mu1 is nothing but mu2 star. No, just a minute. No. So basically the thing is that if you just say that mu2 is equal to mu1 star, then mu1 is equal to mu2 star. Okay, and mu2 star is nothing but 1 by mu1 star. Yeah, then mu1 star, which is mod mu1 square, that will be simply equal to 1. Okay, so then we can just say at best, and same thing will be concluded for mu2, and we can say that both mu1 and mu2 are of modulus unity. That is the best thing we can say. Now, when both are real, then let's say mu1 is equal to 1 by mu2 is equal to some real value mu, then we can show that x1t is equal to mu t by capital T pi 1t, and x2t is equal to mu minus t by capital T pi 2t. Okay. Now here you can remember, you can see mu can be here positive or negative. There is no a priori restriction. Okay. Now if here in this case this is true, that means both of them are individually mu1 and mu2 are real, then what happens? One of them will always increases, of course, x1 or x2 according as whether the mod mu is greater than 1 or mod mu is less than 1. If mod mu is greater than 1, then x1 is exponentially increasing, and if how to say, if mod of mu is less than 1, then x2 is increasing. Okay, like not exponentially, but just to the power, mu to the power t type of thing. Okay, so this is not an exponential, but it's a power increasing. Okay, so increasing with time. So any one of the two is always increasing with time. Okay, and this type of thing simply says that even you are starting from an equilibrium position. Okay, just as the time increases, your displacement will increase. Okay, so even a system at rest in equilibrium is unstable. That means if you just give the system a small perturbation, the system will be going farther and farther by increasing the amount of perturbation. But one thing is there, that if you just start by saying that initial position, that is one thing, is that if you simply say that at t is equal to 0, my pi 1 and pi 2, they are somehow 0. Let's say I am just saying at t is equal to 0, pi 1 is 0. Then no matter what the value of t is, okay, so you can see that, so x1 will always be 0, and the same thing for this. So if you just say that pi 1t and pi 2t, they are 0, okay, then whatever be the value of t, finally these two will be 0. Okay, so that is the thing. And so this type of phenomena is known as parametric instability, and actually this is also known as parametric resonance. Okay, now what are the conditions of parametric resonance will be discussed in the next lecture, or after one lecture. Okay, so when we will introduce the theory of perturbations, okay, then that will be much more clear. Now here my question is, you can see that here something is increasing and we are talking about resonance, but in general when we talk about resonance, in general there is a story of a matching of frequency of something. Can you also here see some matching of frequencies of something? If yes, where? And if no, then it's okay. Okay, just think and try to answer me. Okay, so that's all about the introduction of parametric instability. Much more analysis will be done after theory of perturbation. Thank you very much.